So we are starting our mathematical foundation course. This will be our phase 0. The first module we are going to cover is set theory. Let us start with the exact basics and the definition of what is a set. Now the definition of set is basically a collection of well-defined objects. This is the textbook definition of set. Now, one key thing to notice here is this word, well defined. So basically, a set is nothing but objects with a definition attached to it. Let me give you some examples. See, suppose I just give you 4 superheroes. I have Superman, I have Thor, I have Iron Man, and I have Spider-Man. Now see, this is a set of 4, basically just a set of 4 superheroes, but it has no definition attached to it at the moment. Okay, when I say a set of superheroes, it can have anything. It can have Superwoman, can have Hulk, Daredevil, Punisher, and so many other folks. But see, at this point of time, there is no definition attached to it. So this is just a collection of objects. This is just a collection of objects. This becomes a set when it has a definition attached to it. Plus definition, it will become a set. For example, if I say the definition of this set as 4 superheroes, specifically I'm mentioning 4 superheroes, then it becomes a set. Alright, let us see some more example. For suppose there is a Nike store and I am listing down all the shoes that they are selling in a particular Nike store. Suppose the number of the store, suppose Nike numbers all their stores from 1 to wherever it goes. Suppose the shop number is 178. Now at shop number 178, the collection of shoes will become a set. For example, I have a shop, the shop number is 178, Nike shoes. So if I make a collection of all the shoes in that store, suppose that store has 978 shoes, then this becomes a set. How? This is a collection of objects plus a definition attached to it. What is the definition? Shoes in Nike store 178. Alright. So now we have learned what is a set. Now set, as you can see, we are representing here one by one. Here also we are representing it one by one. So there are multiple ways you can represent a set. Let us see the ways of representing a set. Representation of a set. Okay. The first one that we have to study is a roster form. In this, what happens? Every object of the set is listed in curly brackets. This is one important thing. This term curly brackets. So basically curly brackets, when you see, you mean these signs. So basically all the elements in of the set represented one by one inside curly brackets is a roster form. We use curly brackets to denote a set. Okay. An example of a set in roster form, as we have seen above, this Superman, Thor, Iron Man, Spider-Man, this is a roster form of a set. For example, if I make a set, this one, set of all female superheroes in MCU, then what all you will have? You will have someone like She-Hulk, you will have Wanda, you will have Black Widow, you will have Spider-Woman, Like this, the list continues. At one point, it will end. There is a limited number of female superheroes in MCU. There's a limited number of superheroes in MCU. Okay, so this is what we mean by roster form representation of a set. We represent every object of the set in inside curly brackets, then it becomes a roster form. Next, we will be studying the set builder form. Now, see why this is important is that in the roster form, we can see that it takes a lot of efforts to list down every object of the set. So, what we use in set builder form, instead of listing every object of the set, we will be using the definition of the set to denote the set. For example, if I try to write this same set in set builder form, what I will do? I will just use superhero. The straight line is called such that, basically superhero such that, what is the definition? Now superhero such that superhero is female and in MCU. See, this was my definition of the set. So using the definition, I am writing my set. This form is called set builder form. Now there are some other examples that we can see to understand the set builder form. For example, I can say product such that product is designed by Apple. This is another set where you will have products like your iPhone, iPad, Apple Pencil, MacBook. Like this, it would continue. But see, it took a lot of effort to write everything in your roster form. So, a set builder form is an easy way to denote a set using its definition rather than using the set builder form. Okay. So, the next topic that we have to study now that we know how to represent a set are types of sets. Here we will be studying a few kind of sets. Let me just list them down. First, we will be studying about empty set, singleton set, then we have finite set and infinite set. So this is basically distinguishing between sets depending upon their number of elements in it. Depending upon the number of elements in it. The next we will be studying equal set, equivalent set, disjoint set, and overlapping set. Now, these are basically comparison of sets. The last topic that we will be studying, universal set, subset, proper subset, power set. Okay, these are sets arising from sets. We will understand what it means. Let us start with the first topic that we have, that is basically empty set. As the name suggests, a set that contains no elements. That contains no elements. See, notation, you can either notation is an empty curly brackets or phi. Now, if you mention in the definition of set, we said that there has to be a definition attached to it. Here, see, a definition attached to a collection of objects. Now, what can be the case here? Like, what kind of definition can we attach to a collection of objects such that the collection has no elements? If you can see some example, I can say set of all planets where humans are known to be able to survive in Milky Way galaxy. So currently we do not know any planet where humans can survive. So this set will be nothing but just an empty set or phi. This notation is called phi phi. Alright. Similarly, if I can say some other example, if you want to see collection of, let's see, collection of tigers watching this video. As you guessed it, there will be no tiger watching this video. So again, this set will again be an empty set or phi. Alright. The next example, the next thing that we have to learn is singleton set. Okay, one correction. In Milky Way galaxy, we have to say other than Earth, because Earth is a planet in Milky Way galaxy where we can survive. Then only it will become phi. Okay, next we have singleton set. Now, as per the definition of singleton set, it is a set that contains only one element. See, I can give you some example. This is basically can be said as collection of humans making this video. As you guessed it, there is only one person, me, who is making this video, so this set contains only one element, hence a singleton set. Another example can be planets where human can survive. Human is known to survive. There is only one such planet, that is Earth, our planet. Again, only one element, hence singleton. Next we have finite set. Now, a set, by the name we can guess, a set that contains finite number of objects. For example, the above example that we saw, a collection of humans making this video, this is a singleton set. Planets where humans is known to be able to survive, again singleton set. These two sets are again finite sets. So we can say, note, singleton set implies finite set. Okay, so both of these are finite set. Some more example. Movies released in MCU between between 2016 and 2022. Here if you see, all this set will be a finite set. Why? Because the number of movies between 2026 and 2022 in MCU is a finite number of movies. We can easily quantify them. We can easily quantify them as 100 movies or 20 movies, like that. So basically a set whose number of elements can be quantified is the set to be a finite set. Next we have infinite set. Okay, this is nothing but a set that contains infinite number of elements. Infinite number of elements. Elements are objects. One thing to note here is that the objects of a set are also called elements. One example here could be movies released after 2020. See, I have given one start date but no end date. So I don't know where this ends, and the list of movies at any given point of time can be infinity. It will contain movies like Odyssey, Project Hail Mary. It will just continue, and we don't know like how many such movies have been released after 2020. So one way you can say that the list is not quantifiable. Hence, we call it an infinite set. Okay, going next, we have equal set. Its definition is as follows. Suppose you have two sets, A and B. So, two sets A and B are said to be equal if they have the same elements in them. For example, suppose by some definition you are getting two sets 1, 2, 3 and 3, 2, 1. Now, see here, both of these have the same elements in them 1, 2 and 3. So by this definition, the definition I mentioned above, these two sets are equal. The reason being the elements between A and B are same. Alright. Then next we have something called equivalent set. Equivalent set. Now, two sets A and B are said to be equivalent if they have the same number of elements in them. For example, suppose by some definition you have these two sets 1, 2, 3, 4 and B equal to A, B, C, D. Now, what is the number of elements in set A? It is 4. Set B also 4. Here you can see both the sets have the same number of elements in them, that is 4. So this implies that A and B are equivalent. Alright. Equal set means the two sets have to have the same elements in them, whereas equivalent means that the two sets will have to have the same number of elements in them. Alright. Some things to note here. Equal implies equivalence. What does this mean? If I have two sets which are equal, that is they have the same elements in them, then it means that they're equivalent as well, because if they have the same elements, then they will have the same number of elements as well. For example, see what happens is 1, 2. Suppose I have this A and I have another set 1, 2, 2. As you can see, the 2 is repeating here. Such things are not allowed in a set, so this eventually ends up as 1, 2. Alright. So set A and B have the same elements in them, hence they are equal and equivalent. Alright. Next, equivalent does not imply equal. As we have seen in the example above, set A and B here, they are equivalent but they are not equal, because because even they have the same number of elements in them, the elements are not same. Okay. Next type of set that we have to cover is disjoint sets. Two sets A and B are said to be disjoint if they have no elements common between them. If they have no elements common between them. For example, A equal to 1, 2, 3 and B equal to 4, 5, 6. Here see, none of the elements between A and B are common. No commons. Hence we say that A and B are disjoint sets. Alright. Next we have overlapping sets. You can have two definitions for this. The first one is any set which is not disjoint is overlapping set. Any are overlapping sets. Or you can say two sets A and B are said to be overlapping. Two sets A and B are said to be overlapping if they have at least one element common between them. Example, you have A equal to 1, 2, 3, 4 and you have B equal to 3, 4, 5, 6, which are arising from some definition. Alright. Now see, set A and B, they have two elements common between them, 3, 4. Alright, these are the common ones. And because they have more than one, they have at least one common element between them, we can say that A and B are overlapping.
The next topic that we are going to cover are basically sets arising from sets. The first one we have to identify, we have to study, is basically universal set. Now, what do you mean by universal set? This is a set of all possible elements. See, you can consider it as a set which contains all the elements. You can consider it as a set which contains all possible objects. Which contains all possible objects. So imagine you have a set of animals, lion, tiger, and everything, and a set of numbers 3, 4, 5, 6. Now, if I have a set which contains all such elements, it can belong either to a number or from the animal kingdom or from plant kingdom, anywhere. Such a set is called as our universal set. Notation is U. Next, we have to cover subset. We will actually cover two things: subset and proper subset. Suppose I have a set A, 1, 2, 3, 4, 5, 6. Okay. If I take a few elements out of it, suppose I'm taking 1, 2, 3. Let me call this B. 1, 2, 3. Now, also suppose I'm taking out a set called A even, which is basically the even numbers of the set. Then I'm taking out A odd, which is basically the odd numbers of the set. Now, as you can see, this B, A even, A odd, all of each of the elements of this set are contained in A. From A even also, each of the elements of this A even are contained in A. A odd also, each of the elements are contained in A. So we can say that B is a subset of A. Basically, what it means is each element of B, each element of B is present in A. Okay? Now, one more thing that you need to remember here, or you need to observe here, suppose I have A dash, which is equal to 1, 2, 3, 4, 5, 6. Here you can see my both A and A dash are same. So basically each element of A dash is present in A. if I write it here, each element of A dash is present in A. So this means A dash is also a subset of A. Now, what do you understand by this? Basically, every set is its own subset because each element of the set is present in the same set, obviously. Okay. Now, one more thing that distinguishes a proper subset from a subset is, see all these b equal to 1, 2, 3, a even equal to 2, 4, 6, a or equal to 1, 3, 5. All of these are a proper subset of A. The reason being the number of elements in B, A even, A odd is less than the number of elements in A. Hence, these are called proper subsets. Okay. So basically, you can say every proper subset is a subset. The next and the last topic that we have to study in type of subset are the power set. Now that you have understood what a subset is, so if I make a set of all possible subsets of a set, then it becomes a power set. Definition is as follows. Power set is always defined with respect to a set. So suppose you have a set. Suppose you have a set A. Then set of all its possible subsets is called a power set. It's called a power set. For example, suppose my set A is equal to 1, comma 2. Then my power set is denoted by P of A. P of A is equal to, I will have my set as 1, 2, the empty set, suppose I take nothing out of it, and the set itself. As we have said, every set is its own subset. So this will be my power set. Few more things to note here. Note number of elements in a power set is equal to 2 to the power of n, where what is n? Number of elements in our concerned set. Number of elements in concerned set. If you see it here, suppose I have a set A that contains n elements, 1, 2, n. Okay. Now my P of A will be 2 to the power n. The reason being, see what my aim is to make subset. Now here, every element of this set A can either, suppose I'm making a subset. Okay? So every element of this A can either be in this set or not be in this set. So it has two options, in or out. So so first element has two options, second has two options, up to nth element will also have two options. If I product all of these, what do I get? 2 to the power n. This is the reason or the derivation, like why the power set has 2 to the power n number of elements.
Moving on, the next logical step or the next logical topic to understand is set operations. See, till now we have covered what are sets, some examples, and the type of sets. So the next logical way of going forward is basically to create new sets using given sets. And the way we can create new set given two or more sets, we conduct some operations between sets. What are these operations called? The first one is union. Then we have something called intersection. Then we have something called difference. And we have something called symmetric difference. These are the kind of operations, these are some of the operations that we can apply on two or more given sets. Okay. operations that can be applied on two or more given sets. The first one that we have to study is union of set. Union of two sets. Understand this. Suppose you have two sets A and B. Then union of A and B is the set which contains all elements of A and B with the common elements being repeated only once. Only once. Understand it. See, this part is important. Common elements being repeated only once. Okay, let us understand this using an example. Suppose your set A is 1, 2, 3, 4, and my set B is 3, 4, 5, 6. Now, as per the definition, the union of these two sets will contain all the elements of this of sets A and B with the duplicates or the common elements being repeated only once. First, let us write the first part of the definition. It contains all elements of A and B. Let us just list down all elements of A and B. These are all elements of set A. Next, we will write all the elements of set B. Alright. So this is the first part of the definition. Next part says the common elements should be repeated only once. So here, as you can see, 3, 4, these are repeated more than once, that is twice. So what we will do, we will just repeat them only once. So our set will become 1, 2, 3, 4, 5, 6. So this is nothing but union of A and B. Okay. Notation, this U, or you can write A union B in our case is equal to 1, 2, 3, 4, 5, 6. Done. Next in our agenda is to understand intersection of two sets. The definition follows the same thing, same structure actually. Suppose you have two sets A and B, then the intersection is a set of elements common between A and B. Okay, understand this. We will use the same definition, same example. 1, 2, 3, 4, and B equal to 3, 4, 5, 6. Our aim is to find the intersection of this. As per definition, the intersection will be a set which has elements which are common between A and B. Now see, A has 1, B doesn't have 1, A has 2, B doesn't have 2, A has 3, and B also has 3. See, these are common. 3. Again, 4 is common. 5 and 6 are not present in A. So basically this 3, 4 is our intersection. Notation and inverted U. So basically what we will say, A intersection B is equal to 3, 4. Alright, next we have difference of two sets. Again, similar structure of our definition. Suppose you have two sets A and B, then A difference B, or you can also say it as A minus B, is the set of all elements in A which are not in B. So basically from one set we are removing all the elements of the other set. We will use the same example as above. A equal to 1 2 3 4, B equal to 3 4 5 6. Okay, now as per definition, A minus B, we are trying to find A minus B. Okay, as per definition, all elements of A which are not in B. So 1 is in A, not in B. 2 is in A, not in B. 3 is in A, but it is, sorry, 3 is in A, but it is also in B. So we can't write 3. 4 is again in A, but it is also in B. So again we can't write 4. So 1 comma 2 will be our A minus B. Okay. Now understand this. Basically, if what the difference of two set is, you have a set A, and from this set A you are removing all the elements which are present in set B. So as per this example, A minus B will be equal to 1 comma 2. Okay. The next topic is symmetric difference of two sets. Now this basically uses a combination of difference of two sets and union of two sets to arise at a new set. So the definition we will try to follow the same path as before. Suppose you have two sets A and B, then the symmetric difference is the set of elements which are present in either A or B, but not in both. See, so basically we will take the same example. 1 2 3 4, B equal to 3 4 5 6. As per definition, we want all the elements which are either in A or B but not in both. See, we can see 1 comma 2 here and 5 comma 6. These are not present in both of them, but they are present in A and B. So the answer to the symmetric difference will be 1 comma 2 comma 5 comma 6. Alright, or you can also see it as a few of the other operations that we have studied. What we are doing A union B. We are first writing down all the sets here present here. Sorry, all the elements present here, 1 2 3 4 5 6, and we are subtracting A intersection B. Okay, what is our A intersection B? 3 comma 4. So and what will we get when we do A union B minus A intersection B? We are getting 1. See, we just have to remove these two, right? 1 comma 2 comma 5 comma 6, which gives us the same set which we got using the definition. Okay, the next topic for us to understand is something called Venn diagrams. See, previously we understood what sets are and how can we represent sets using a roster form and a set builder form. So Venn diagrams are another way of representing sets. It basically represents sets virtually. Okay, so in Venn diagram, what we do, we basically create a structured container for sets. What are these containers? These containers can be two things. It can be either your squares or closed curves slash circle. One thing I need you to remember, or I need you to note, is squares are universally, or squares are generally used for universal sets, whereas these closed curves or circles, these are used for any other set other than universal set. any other set. All right. Let us understand this with an example. I will try to represent various kind of sets or various sets using Venn diagrams. Okay. Suppose I have a universal set which contains these values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want you to know one more thing. See, these are basically natural numbers between 1 to 10. So another way of representing this is n10. See this Times New Roman kind of n. This basically represents natural numbers up till 10. Okay. All right. Now from this universal set, we are making two sets out of this. A equal to let us consider it all the odd numbers 1, 3, 5, 7 and 9. Then we make B as all the even numbers 2, 4, 6, 8, 10. Alright. Now as I had mentioned before, squares usually used for universal sets. Okay. So this is a square. This is not a square basically. This is basically a square slash rectangle. So as I had mentioned earlier that we use square for universal set, you can also add the fact that we can also use rectangles. Basically any kind of rectangle we can use for universal sets. So see, as I also mentioned earlier, these Venn diagrams are basically containers for sets. Now this rectangular container, it contains all these elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, and we are calling it U. Now as you have seen, we have to make two more sets, A and B. And these sets which are not universal set are represented using closed curve or circle. Okay, so let me make one closed curve using this pink color. So it contains all the odd numbers. So let us find all the odd numbers and put them in a container. That container will also become one part of the Venn diagram. See, starting with 1, 3, 5, 7, 9. See, this is a closed curve which contains all the odd numbers. All right, so this is my A. Also I have to make set B. So this contains all the even numbers starting with 2, 8, 10. Then we have 4 and 6. See, this is representing set B. Alright, see, both of those are closed curves inside U. So this is how we are representing A and B. So this is a Venn diagram, but it is not structured yet. Not structured. So now what will be our aim? We will try to give it a structure. So step 1, let us okay, one more thing. Now what steps we take to make this a bit more structured? Step 1 that we can take, instead of using the entire elements of the set in a roster form, we will use the name of the set. Next, what we will do, we will use circles to represent the sets inside universal set. Alright, let's make it a bit more structured. See, this is what we have made. Now in this, let me add the names as we saw in the previous example, as we saw in this, that to make the set more, to make the Venn diagram more structured, we have to use name of the sets and use circle to represent the sets inside universal set. See, we have used circles to represent sets inside universal set. Now we will give them a name. This rectangle is a U, our universal set. These two circles are named as A and B. Alright, now to get a bit more detail, this step is optional. You can also write what all sets are included inside A and B. For example, we have 1, 3, 7, 5, 9. Here we have 2, 4, 6, 8 and 10. Alright, all done. Now let us see some more examples that we can write using this. For example, suppose I include another set. We have u equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alright. I write set A as all the odd numbers 1, 3, 5, 7, 9, 11. My set B as 2, 4, 6, 8, 9, 11. Now, in this case, how will we represent the set? Alright. Now, our aim to represent this using Venn diagram. But here you can see 11 is common between them. Here see there was nothing common between A and B, but here we have the set 11. In this case, what we will do, see this portion that is overlapping, we can add 11 here. This is just an example. I'll just try to draw the sets as well. Let me make a rectangle. We will follow the same steps as before of making this UAB, the new U, A and B in the form of a Venn diagram. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. Now let us make the closed curves. I have 1, 3, 5, 7, 9 and 11. Sorry, 9, 7. Here I have 5, 3 and 1. This is my set A. Next we will make our set B. Set B also contains 11, 10, 6, 8, 4, 2, and we have to close it. See, this is my set B, but as you can see, it has become so complicated. So what we will do, we will try to make it a bit more structured. Same, we have to make it structured, same as before. We have to make it structured. How? We will use name of sets and we will use circles. Alright, now how will we do that? Step 1, make our universal set. Alright, this is U. Okay, inside this I am making a circle for A and for B. But see, what is the issue here? 11 is common in both of them. So basically these two sets will be overlapping each other. So let me make two overlapping sets. This is A. Similarly, I'm making B here. Alright. Let me just add a bit more definition to this using shapes. Alright. See, now we have two overlapping sets, A and B. And this common element here is basically 11. Here and what we'll have here, we will have 1, 3, 5, 7, 9. Here we will have 2, 4, 6, 8, 10. So this is a way you can represent two overlapping sets in Venn diagram. Alright. Similarly, what if you have one set inside of another? For example, instead of A and B as 1, 3, 5, 7, 9, 11 and 2, 4, 6, 8, 9, 11. Okay, it should be 10 here. Alright, now that we are done with overlapping sets using Venn diagram, let us understand how will we show subsets using Venn diagrams. Suppose I have a set U, which is basically all the natural numbers up till 10, and my set A is equal to 2, 4, 6, 8, 9, 10, and my set B is equal to 4, 6, 8. Alright, we have both A and B. Here you can see B is a subset of A. See, 4 common in both, then 6 is also common in both. You can see that 6 is common in both, 8 is also common in both. So basically, we will first, while making the Venn diagram, we will first have a universal set. Alright, then we will have one set A inside our universal set, which will basically be 2, 4, 6, 8, 10. Then basically inside this set A, we will have our set 4, 6, 8. See, and if we give some structure to this, what do we get? This is the structured output. This is the structured Venn diagram actually. So we have first have our universal set U, then we have a set A, and inside this set we have the set B. So this is the way you represent a subset using universal sets. Sorry, a subset using Venn diagrams. Alright, now that we have understand Venn diagrams, let us see some of the set operations in Venn diagrams. The first one that we have is union. See, then we will say intersection. Then we will see difference. And finally, we will have symmetric difference. Alright, let's start one by one. Let me just make the set. We will use the one set as universally to understand this. Alright, so now we have two sets, A and B. The first we will be seeing A union B. A union B. As we know, A union B is basically the combination of all sets in A and B with the repetitions or the common ones in A and B repeated only once. This is a definition of a union. So by this logic, we will have all the elements in A as well as B. Let me just draw them. So this portion will basically just be A union B. All the elements in A and B with the repetitions being written only once in the final set A and B. In the final set A union B. Alright, this entire portion. Similarly, if we see A intersection B, what do we have? What do we mean by A intersection B? Okay, let us see A intersection B. Now, A intersection B is basically the set of elements common between A and B. Common between A and B. So by this logic, only this portion is common between A and B. Hence, this region, it represents A intersection B. This region, it represents A intersection B. Alright. Similarly, the next one we have A minus B. Definition, what does it mean? All elements of A not in B. See, now if you see this diagram, only the intersection part is basically in B. Hence, we can say this region will represent A minus B. A minus. The next one we have is symmetric difference. Alright. What do we mean by symmetric difference? By definition of it, we have symmetric difference. So by the definition, what do we have? All elements of A and B, all elements of A and B which are not in both. So basically the entire A union B except this region. So what will it be? If we try to draw it, this will basically be this region. So this region, this entire thing except the middle portion, the intersection portion, will be our symmetric difference. The entire set A union B except the ones common between them. Alright. The next topic we have to finish is cardinality. This is very simple. This basically represents the number of elements in the set. For example, suppose I have a set of cold drinks. So what all can I have here? I can have Mirinda, I can have Fanta, I can have Coca-Cola, I will have here Pepsi. Suppose these are all the sets. These are all the elements I have. Now the cardinality of this set will be 4. Similarly, if I have an empty set or 5, the cardinality will be 0. Similarly, if I have a singleton set which contains only one element, that is basically me, the cardinality will be 1. Alright, this is a very simple topic. Cardinality is basically the number of elements in the set. The next topic that I want to focus on, and it's kind of pretty important, is basically countable and uncountable sets. Now see, every set can be categorized as countable or uncountable. Okay, so set can be of two types. One is countable, another uncountable. Now in countable, again it can be of two types. It can either be finite or countably infinite. We'll understand all these. Alright, let's start with the first one. Countable set. It has, see, a set will be called countable if one case is satisfied, that is, it is finite. What do you mean by finite? That its cardinality is a natural number. Alright. One other condition which makes a set countable. Okay, wait. One other condition which makes a set countable is countably infinite. Let's understand this. Suppose you have a set of integers. Sorry, a set of natural numbers. 1, 2, 3, 4 up to infinity. Now suppose you have a hotel room, or sorry, suppose you have a hotel which has infinite number of rooms. Alright, okay. Now suppose suppose you have a hotel with infinite number of rooms. Now if you are able to give one room to each of these elements, then we call that set as a countably infinite set. Let us understand this with an example. Okay, first example, natural numbers. Okay, before starting with the example, suppose that we have a hotel which has rooms numbered in natural number. Okay, what are the numbers of the room? You have a 1, 2, 3 up till it goes out to infinity. For every number that you can think of, the largest number you can think of, there will always be one room more than that. That is a condition for this hotel. Now we will go set by set. First one, we have natural numbers. natural numbers. Now suppose for each number you are able to find a room in this hotel, then we can call that natural numbers are countably infinite. Alright. Now what are my natural numbers? 1, 2, 3, 4 goes to infinity. Now suppose I give this natural number room number 1, this natural number room number 2, this natural number room number 3, this natural number room number 4, and for every natural number I give it a room of the same number. Alright, so this way I am able to give one room to each natural number. So by this condition, by satisfaction of this condition, we can say natural numbers are countably infinite. Next, let's go on to whole numbers. Alright, now what are whole numbers? Let me represent it by W. I don't know what it is. This is 0, 1, 2, 3, infinity. Alright, now see, suppose I give the plus 1th room to each of the whole number. Room number 0, whole number 0 gets room number 1, whole number 1 gets room number 2, whole number 2 gets room number 3, then whole number 3 gets room number 4, and for x whole number I give them the room x plus 1. This way for each whole number I am able to assign one room in our hotel whose numbers are marked by natural numbers. So by this explanation, whole numbers are also countably infinite. Alright. Next, let us see integers. Okay. Now, integers, these are basically, it goes on from minus infinity to plus infinity. Alright. Here what I can do, I can give room number 0, I can give the integer 0 the room number 1, integer 1 the room number 2, integer minus 1 the room number 3, integer 2 the room number 4, integer minus 2 the room number 5, integer 3 I can give the room number 6, integer minus 3 I can give the room number 7. So basically if I have the x integer I can give it the room 2x, and if I have the minus x integer I can give it the room 2x plus 1. This way for every integer I am able to provide one room in our hotel whose numbers are marked by natural numbers. So by this logic, integers are also countably infinite. Similarly, you can also check or try to find how rational numbers are also countably infinite. Alright. Now, next comes uncountable numbers. Uncountable set. Okay. So basically any set, this is a definition, any set which is not countable is uncountable. This is a very simple negation of countable kind of definition. So basically, if you have a set where you are not able to assign a unique room to each of its members or each of its elements, then the set is called uncountable set. Some of the examples are irrational numbers, the set of all irrational numbers. Then set of all real numbers. Alright. The major reason for this is because we don't know how many numbers are there, because we don't know how many numbers between two irrational or real numbers. This is one of the major reason why this happens. But this is a proper definition. This is a easy definition of uncountable set. Any set which is not countable is uncountable. This is basically the negation of countable. Alright, so at this point we have finished set theory.